In this video, we're going to have a look at proof by induction. Now, it's quite a complicated topic, and it's really only one that, in my opinion, can be explained by just doing an example, then explaining after we've done the example what we've actually done in each step. So you might be confused as we're going through it, but stick with it till the end, because it'll be worth it. Right, so, prove by induction that for n being a member of a Z+, that's the member of all positive integers. So for n being in 1, 2, 3, 4, etc. Show that f of n, which is 5 to the power of n plus 8n plus 3, is divisible by 4. Okay, so step 1 is always prove true for a base case, i.e. the lowest possible value of n. So prove true for a base case. So the lowest possible value of n here is 1. So we're going to let n equal 1, which implies f of 1 equals 5 to the power of 1 plus 8 lots of 1 plus 3 equals 16, which clearly is divisible by 4 given what we know about maths. However, in proof questions we'll really spell that out. So equals 4 times 4, therefore is divisible by 4. Now at the end of each step we've got to conclude properly. So everything I'm writing in blue here is necessary to get all the marks in the exam. You might think that it's going a bit overboard, but I 100% guarantee you need to write this to get the marks. So therefore is divisible by 4. So we can say therefore true for n equals 1. So this statement that we're trying to prove here is true when n equals 1. Right, now the next step, and this is the bit that gets people initially, so we'll come back to this and explain it later, but we're going to assume true for n equals k. So again, everything I write in blue is necessary to get the marks. Everything I write in red is just instruction for understanding and explanation. So we're going to assume f of k equals, and it was equal to 5 to the n plus 8n plus 3. So 5 to the k plus 8k plus 3 is divisible by 4. And you need to write that to get the marks. So now step 3. And this is the bit that's quite difficult to understand. So consider f of k plus 1 take f of k and show this as a multiple of 4 using assumption. So what we're trying to do here, we've already assumed that f of k is divisible by 4. We assume that here. So if we perform this subtraction here, f of k plus 1 take f of k, if this also appears to be a multiple of 4, the only way that can happen is if both numbers are multiples of 4. The only way that you can subtract two numbers, one of which is a multiple of 4, and end up with a multiple of 4, is if they're both multiples of 4. So for example, I've got a multiple of 4, 16, and I take away a non-multiple of 4, I get a non-multiple of 4. However, if I take away a multiple of 4, I get another multiple of 4. So by that logic, if I subtract these two and find that they're a multiple of 4, then both numbers must be a multiple of 4, given that, by our assumption here, f of k is also divisible by 4. Now, the strange thing about that is we don't know whether this statement is true yet, but we'll come back to that in a second. We've assumed it's true, so we're going to pretend it is for now, and we'll come back to where that fits in a little while. So first of all, f of k plus 1, take f of k, equals, okay, so let's sub in k plus 1 into the f of k function. So we get 5 to the k plus 1 plus 8k plus 1. 8 lots of k plus 1 plus 3. Then take f of k. So brackets are important here. We're taking away all of this term, which is 5 to k plus 8k plus 3. And then simplifying that. So our aim here is to prove that this here is a multiple of 4. Now, a good strategy in doing this is to try and make the indices of terms the same as in the assumption step. So 5 to the k plus 1, that's a power of k plus 1, which is different to the power in the assumption steps, which is just simply k. So we can turn this into just a power of k by rewriting it as 5 times 5 to the k. Now this is equivalent because that's 5 to the 1 and that's 5 to the k. When we times things together, we add the powers, which gives us k plus 1. So that is equivalent to the term above. So simplifying further, plus 8k plus 8 plus 3, take 5 to the k, take 8k, take 3, and a bit of simplifying can be done here because the 3, take the 3, disappears, 8k, take 8k, disappears, and here we've got 5 lots of 5 to the k, take away 1 lot of 5 to the k, which is equal to, well, 5 lots of 5 to the k, take 1 lot of 5 to the k, is 4 lots of 5 to the k, so 4 lots of 5 to the k, and then there's a plus 8. There's the plus 8 there. So equals, well, we take out a factor of 4, we get 5 to the k plus 2, which is divisible by 4. So what we've shown is if f of k is divisible by 4, so we're assuming that that's true. We don't know whether it is yet, but we are assuming that that's true. Then the difference between them, if we can prove that's divisible by 4, then this must be divisible by 4 as well. F of k plus 1 must also be divisible by 4 if the difference between f of k plus 1 and f of k is also divisible by 4. So again, I must stress, we don't know whether this statement's true yet, we're just assuming it is. But if it is, then this must be divisible by 4 as well. Well, actually, let's go back to our initial step here. And we're told what we said what we're going to do here is prove that's true for a base case n equals 1. Well, we've done that here. It is true for n equals 1. So we've proved that if it's true for one case, then it's true for the next. Well, here, if it's true for the first case, this step here says that's true for the next one on as well, for n equals 2. Now we know it's true for n equals 2, it must be true for the next one, n equals 3. Now that's true for n equals 3, it must be true for n equals 4. So we've proved if there's any one particular case we can prove it's true for, i.e. f of k here, then it must be true for the next one by what we've done here. So step 4, we're going to conclude. So if true for n equals k, then also true for n equals k plus 1. So again, we don't know whether it's true yet, but the killing blow that we're going to deal now is, since true for n equals 1, and again I want to stress here, If it's true for a number, then it's true for the next. So it's true for n equals 1, so it must be true for n equals 2. If it's true for n equals 2, it must be true for n equals 3, etc, etc. Since true for n equals 1, then by mathematical induction, it must be true for all integers n greater than or equal to 1. And everything I've written in blue there is the bare minimum you need to get full marks in an exam. All of that's needed. Anything in red is just instructions for the purposes of understanding, but all of the blue writing is needed to get the marks in an exam. For more videos like this, subscribe to our YouTube channel, and to find out more about our Skype tuition and revision courses, go to A-levelmathsrevision.com.